We're going to learn how to draw ray diagrams for spherical mirrors. In a later video you'll learn how to do ray diagrams for lenses, but we like to start off with mirrors. There are some important things you need to know about our setup here. We have a curved mirror drawn here. This is a concave mirror, otherwise known as a converging mirror. It's called a converging mirror because what it can do with parallel light rays is converge them through the focal point. So the important points for us are the focal point and the center of curvature. Here's the focal point, here's the center of curvature. Drawing a ray diagram, you have to start off with an object, and the object we like to use usually is just an arrow. So I'm going to draw an arrow, and I'm going to start off by drawing this out here. That's going to serve as my object. To figure out where the image is going to be created and what it's going to look like, we start with our object and we draw light rays that emanate from the tip. Two very special rays are the ones that are going to allow us to find our image. We really actually only need 2 rays. A lot of methods will show you 3, which is fine, but we really only need 2. And I'm going to start off by taking a light ray that starts at the tip and goes out parallel to the principal axis. That's the line that passes between the center point and the focal point. And on a converging mirror, any light ray that comes in parallel to that axis will exit through the focal point. Now, the other one would be a light ray that comes in through the focal point, and any light ray that comes through the focal point and hits the mirror is going to come out parallel to the principal axis. Now, determining where the image is going to be is a matter of taking these 2 outgoing rays and tracing them back to where they converge. The place where they converge is this spot right here, and that means that my image is going to be looking something just like that. You notice we draw the tip and then we go connect back to the principal axis. That's the way this always works. What this shows me is that the image that I've created, first of all, you might notice it's upside down. We would call that an inverted image. You might also notice that it's smaller than the original. We call that a reduced image. And finally, all images that are inverted are what we call real images. This is on the real side of the mirror where the object exists, and so we call it a real image. Those are the characteristics of this image. Now, what happens if I take and move my object in closer? The same exact rules apply for finding the image. I'm going to take an arrow from the tip to the mirror and out through the focal point. Now I'm going to go through the focal point to the mirror, something like that, and come out parallel. Here are my outgoing rays, and they converge at this spot right here. That means I'm going to draw my image from that point to the principal axis. And now let's look at the properties of this image. First of all, it's inverted again. It's also, this time, as opposed to being reduced in size, it's enlarged in size, so we call it an enlarged image. It's also still on the real side of the mirror, so it's a real image. So far we've seen 2 image types. If we're out beyond the center point, which is 2 times the focal length, it's reduced in size. If it's between the center point and the focal point, it's enlarged in size. But otherwise, they're both real and inverted images. Let's see what happens if we bring our object inside the focal length. Now, this is where it gets a little weird. The first ray isn't actually that hard to do. I go in parallel, strike the mirror, and come out through the focal point. That's what we did before too. Here's where it gets strange. You can't go from that tip through the focal point and go towards the mirror, can you? You can't do it. What you can do, though, is draw a line that connects the focal point, the tip, and the mirror. So I'm going to draw that line. Okay? Now, any ray that follows that line from the tip to the mirror will come out parallel. So it's this, instead of going through the focal point, is going away from the focal point. So let's see what that looks like. If I go from here to the mirror, I will come out parallel. Here are my outgoing rays. Here's the problem. Where do they converge? And the answer is, well, not on this side of the mirror. So if I trace these back, I'm going to see how good I can do with this. So something like that, you can see they do converge. They just don't converge on this side of the mirror. And so my image is going to look like this. Now this is significantly different than the image we created before. This image is not inverted, it's upright. It's also enlarged, it's bigger than the original, but this time it's on the other side of the mirror. We call this the virtual side of the mirror. When you guys did your lab on plane mirrors, all the images were virtual. Now we are going to look at the ray diagram for a diverging mirror. This is a mirror that is curved in the opposite direction. The focal point and the center point are on the other side, the virtual side of the mirror. So what we're going to do is we're actually going to follow the same principles that we had before, and we're going to see what happens. So starting off with a ray that comes from the tip and goes to the mirror. Now this ray will not pass through the mirror and through the focal point. What it will do is diverge out and away from the focal point. So I'm going to draw a line that connects the focal point to the place on the mirror and goes away. Okay, so my outgoing ray is going to look like this. Okay, it's going to bounce off like that. The other one we're going to do, remember before we'd go through the focal point or away from the focal point and then come out parallel, but this time we're just going to go towards the focal point. I'm going to go towards the focal point. Now, that obviously is not the path that the light will actually take. It's going to hit the mirror and bounce off. But what it's going to do is hit the mirror and bounce off parallel. The way we could summarize this process is I always say there's two rays. In parallel, out focus. In focus, out parallel. So our first ray was in parallel and out away from the focus. The second ray was in towards the focus, out parallel. Now once again, it's where these rays converge that we're going to see our image. So this ray that is up here converges, seems to go back towards the focal point. The ray over here converges straight back to this point here. And our image, I'm going to do this one in a different color, is going to be right there. That is going to be my image. Compared to our original, this image is upright, it's reduced in size, and it's on the virtual side of the mirror, and so it's a virtual image. Now what I want to do is I'm going to see what happens if I move that object closer to the mirror, but I'm not going to erase this time. What I'm going to do is add on. And so I'm going to take this and I'm going to move it much closer to the mirror and see what happens. My first ray would be in parallel, out focus. So that one's already taken care of. The one I need to do now is the one that goes in focus, out parallel. Now this time, still going towards that focal point, we hit up higher. So if I trace that down, I hit the mirror up here and bounce out parallel. The convergent point for that, going straight back, is now here. And I will see this object image over here. The significance of this is moving the object around does not change the orientation, the magnification, or the type of image. In other words, it's still upright, it's still reduced, and it's still virtual. This is actually the only type of image you can create with a diverging mirror.